We've stated all the vector calculus theorems. Now let's see how they fit together. Okay, so in 3 dimensions, there are 4 fundamental types of shapes. We have points, which are just sort of visualized as dots in space. We have curves, which are sort of one-dimensional objects that connect points to one another. There are surfaces, which in general are sort of non-linear, 2-dimensional shapes. And there are solids, which are sort of the 3-dimensional domains. So each one of these 4 types of shapes plays an important role in at least one of the 3 vector calculus theorems. And when we manipulate surfaces, or when we think about parts of them, one thing we do is we look at the boundaries of a surface or of a shape. So the boundary of a shape is always a lower dimensional shape. So for instance, let's say that we were studying a solid, and we decided to take the boundary of that solid. Well, the boundary of a solid is a surface. And let's say we took some ordinary surface and took its boundary. Well, the boundary of a surface is a curve. And then what is the boundary of a curve? Well, curves connect points, so the boundary of a curve would be points. So these 4 fundamental types of shapes are related to one another via boundaries. And the idea is that when we take the boundary of a shape, we produce a new shape with a lower dimension. And there's also this adjective closed that we've introduced. And the idea behind a closed shape is that a closed shape is a shape without a boundary. So the idea here is that when we take the boundary of a solid, we produce a closed surface, and that closed surface has no boundary curve. When we start with a surface and take its boundary, we are studying a closed curve, and that closed curve itself has no boundary because it is not connecting 2 points. So what we have here is a diagram that's connecting different concepts to one another via the notion of a boundary. And in this diagram, when we take 2 steps, we end up with nothing. The boundary of a solid is a closed surface, and the boundary of a closed surface is nothing. The boundary of a general surface is a curve, a closed curve, and the boundary of a closed curve is nothing. So we have a chain of connections here, and because in this chain of connections, when we take 2 steps, we produce nothing, we call this sequence exact. And we've seen the notion of an exact sequence before. Namely, we've seen the exact sequence when we discussed the operator exact sequence. Remember, the notation here, script C of R3 is the notation for all scalar fields on R3. Script X of R3 stands for all vector fields on R3. So what we saw was that we could introduce 3 operators on scalar and vector fields. The first operator we introduced was the gradient of a scalar field, and the gradient of a scalar field is a vector field. We then introduced the notion of the curl of a vector field, and the curl of a vector field is a new vector field. Finally, we introduced the divergence of a vector field, and the divergence of a vector field is a scalar field. We further said that this sequence of operators is an exact sequence. This means a couple of important things. For one, if we take 2 steps in the sequence, we always get 0. What this means is that the curl of the gradient of a scalar field is the 0 vector field, and also that the divergence of the curl of a vector field is always the number 0. We also gave construction arguments or formulas in class. So we know that if we take the curl of a vector field, that actually means that it came from a gradient of a scalar field. And Poincaré's lemma gives us an explicit way to find a scalar field that produces our vector field as its gradient. We also saw that if we take the divergence of a vector field and we get 0, then that means that the vector field came from the curl of another vector field. And Poincaré's lemma gave us a method for constructing our vector field whose curl was the vector field we started with. So the exact sequences are not only organizational tools that help us sort of remember how the operations work, they're also organizational devices that help us construct and organize mathematics. And if we think for a moment, we realize that the two concepts that we've just constructed sort of match up in some sort of nice dualistic manner. We saw that there's this exact sequences of shapes where if we take the boundary of a solid, we produce a surface. If we take the boundary of a surface, we produce a curve. And if we take the boundary of a curve, we produce points. Well, if we stack that exact sequence moving to the left on top of the operator exact sequence, we get a nice matchup between concepts. So here we're sort of equating points in space with scalar fields. We're replacing the boundary operator on curves with the gradient operator. We're making analogies between curves and vector fields. We're making analogies between boundaries of surfaces and the curl operator. We're making analogies between surfaces and vector fields, and boundaries of solids to the divergence operator. So there's a nice sort of pairing that occurs here. And I want us to think of this pairing in three different ways. So there's sort of three sections of these sequences. There's the first sort of pairing, which is relating the concept of relating a boundary of a curve to points to the concept of taking the gradient of a scalar field and producing a vector field. There's also an analogy in the second section of these exact sequences. Here we're somehow equating the idea of taking the boundary of a surface and producing a curve to the concept of taking the curl of a vector field and producing a new vector field. Finally, we have analogies between the concepts of taking the boundary of a solid and the concept of taking the divergence of a vector field and producing a scalar field. So other than the fact that these line up nicely in the sense that I have a sequence with 4 nodes up top and a sequence with 4 nodes on bottom, how does this relate to the vector calculus theorems? Well, we have 3 vector calculus theorems. In the first vector calculus theorem we learned, we were studying the fundamental theorem of line integrals. This was actually from months ago. And at its core, what the fundamental theorem of line integrals says is that if we take a path integral of the gradient field of a scalar field, this is the same thing as evaluating the original scalar field at the endpoints of the curve. If we can abstract that language for a moment, we might see an analogy between this theorem and the other two. The way that I like to read this theorem says that if we take an integral of the gradient operator over a curve, what we end up doing is evaluating the original scalar field on the boundary of that curve. After the fundamental theorem of line integrals, we did a bunch of new things, and then we learned Stokes' theorem. Stokes' theorem rigorously says that the surface integral of the curl of a vector field over a surface is the same thing as the work done by that vector field on the boundary of the surface. If we can abstract the language here, we find an analogy to the fundamental theorem of line integrals. The way that I like to think of the language here is that taking an integral of the curl operator over an object is the same thing as integrating the original vector field over the boundary of the object. This is sort of exactly how the fundamental theorem works. Integrating the gradient operator over an object is the same thing as evaluating the original field on the boundary of the object. With Stokes' theorem, integrating the curl operator over an object is the same thing as integrating the original vector field over the boundary of the object. Finally, we have the divergence theorem, which says that the triple integral over a three-dimensional domain D of the divergence operator of a vector field is the same thing as the flux of that vector field through the boundary of the three-dimensional domain. Abstracting the language here proves useful as well. The language here, when abstracted, says integrating the divergence operator over an object is the same thing as integrating the original vector field over the boundary of the object. So what we're seeing here is that even though these are three totally different theorems that apply in totally different contexts, there is some sort of unifying theory lurking in the background. Each one of the statements of these three theorems can be, we can take the language of them and abstract it in such a way that they're all saying the same thing. When we integrate one of the operations on vector fields over some sort of object, what we're really doing is taking the original field and evaluating on the boundary of the object. And this is compatible with the pairs inside of, the sections inside of our pairs of exact sequences. So each theorem here pairs with one of the sections of our exact sequences. So our exact sequences can be organized like this. Boundaries of solids are surfaces, boundaries of surfaces are curves, and boundaries of curves are points. Down here, the gradient of a scalar field is a vector field, the curl of a vector field is another vector field, and the divergence of a vector field is a scalar field. Well, the first section of our exact sequences here related the concept of taking a boundary of a curve and obtaining points to the concept of taking the gradient of a vector field in producing, or gradient of a scalar field in producing a vector field. Well, what we're finding here is that in the fundamental theorem of line integrals, what we end up doing is taking the gradient of a scalar field to produce a vector field, and then we integrate over an object, and that object is a curve. The fundamental theorem says that's the same thing as taking the original field, which is a scalar field here, and evaluating on the boundary. So we have sort of the picture on the right-hand side, which is gradient, which is a vector field being evaluated on a curve, being equated to looking at the original field, which was a scalar field, and evaluating on the boundary, which consisted of 2 points. What about Stokes' theorem? Stokes' theorem can be studied by looking at the middle of our exact sequences. Stokes' theorem says that integrating the curl operator over an object is the same thing as calculating the work done by the original vector field on the boundary. Well, again, we sort of have a natural way of matching up these two parts of the equation with the 2 parts of our exact sequence. On the left-hand side of the equation, we are integrating the curl operator over a surface. So down here, when we take the curl of a vector field, we produce a new vector field over here, and that vector field is interacting with the surface. Stokes' theorem says that instead of calculating the flux of the curl over the surface, we can instead calculate the work done by the original vector field on the boundary. Well, down here, the idea is that if we started with the original vector field, we could have calculated the work done by that vector field on the boundary of our surface, which was a curve. So integrating the curl on a surface is the same thing as integrating the original vector field on the boundary curve. Finally, we have the divergence theorem, which matches up with the last section of our exact sequences. The divergence theorem says that integrating the divergence operator on a domain is the same thing as calculating the flux of the original field over the boundary. Again, we have a natural way of matching the 2 parts of this equation with the 2 sides to this exact sequence. On the left-hand side of the divergence theorem, we're looking at the triple integral of the divergence operator over a solid domain. So when we take the divergence of a vector field, we produce a scalar field, and we can see how that scalar field interacts with a solid domain. Well, when we take the boundary of that solid domain, we get a surface. So the boundary is a surface. And what the divergence theorem says is that if we were to integrate the divergence operator over the original solid, that's the same thing as taking the original field and calculating its flux over the boundary surface. So in each vector calculus theorem, what we can do is we can study that theorem by comparing which part of our exact sequence the theorem corresponds to. People might note here that we're not mentioning Green's theorem, but I really do view Green's theorem as a special case of Stokes' theorem, where the surface itself only lives in the xy plane. So in fact, the theory that we're presenting here includes Green's theorem, because Green's theorem is really a consequence of Stokes' theorem.